Morning, everyone. Today we are wrapping up our lessons on how to create normal distribution bell curves with regard to our quant section of the research class. So this is going to be a very short PowerPoint, but there is an exercise in here that I need you to try and practice. This is important because you all need to do a quantitative project, and so you need to make sure that you know how to do this math. And you need to know, sort of just understand, why bell curves are significant, what they can do to help us describe data as well as predict future data, which is something I did completely in the last video. I'll put the link to the last video below because that's going to help you with the math part if you are still struggling with it. I'd also encourage you to do the math exercise on your own and then check in with a classmate to see if you and the classmate got the same numbers. Okay, so here's the math exercise for today. All right, with this data set here at the bottom, I want you to find the mode, the median, and the mean. How to find all those is in the video down below, so make sure you revisit that video. You need to find the deviation for each point of data from the mean. So once you discover what the mean is, you add up all these numbers. Whatever that answer is, then you divide by how many sets of data there are, which there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So add all these up, divide by 15, right? And that's going to give you the mean. That's the middle number on your bell curve, all right? Then you take each set of data, 88 minus the mean, 91 minus the mean, 93 minus the mean, right? Now you have a new set of numbers, okay? You take all those numbers and you square them. You add up all of these new numbers that have all been squared. Then you divide by 15 again. That gives you the variance. You take that variance, you find the square root of it, and that'll give you the standard deviation, all right? Then you need to draw that onto a bell curve, all right? 1, 2, and 3 standard deviations following the 68, 95, 99.7 rule. If any of this is confusing you, go down to the previous video where I describe it in far more detail. All right. So do this math exercise on your own on Friday when we come to class. I'm going to ask you for the numbers that you got. All right. So that's what we're going to start off with in class on Friday is with these numbers, and you all creating a bell curve. So this is a normal distribution bell curve. So you find the mean of all those previous numbers. The mean goes right here at the 0 mark, right, which is the mean. You find the standard deviation, plus and minus 1 standard deviation, 2 and 3. 68% of all your data is going to fall within 1 standard deviation, right? So what we're going to pretend for a second is those previous numbers, we're going to pretend that those are test scores, all right? So we're going to figure out whether or not, whatever your test score is, does it fall within 1, 2, or 3 standard deviations of the classroom mean, all right? This is the ways in which, professors can also go about when we talk about curving grades, right? Whether or not a test grade is going to be curved because the test was too hard or too easy. Professors are essentially using some sort of form of a normal distribution bell curve to figure out, how close you are to the class average, right? There's obviously going to be a middle number, like this class average, a class average of 75 or whatever the mean is, right? But then they're going to be able to figure out, how close within 1 or 2 standard deviations are you of the class average, or are you very well overperforming? You have like a 99%, so you're way in the top, 0.1%, right? Or are you far, far below? You're down to like 40% on the test, so you are way below the class average, right? So this helps professors sort of figure out what they need to do as far as individual instruction with students with regard to where they're falling at on this normal distribution bell curve, all right? So to use those numbers, let's pretend like they're test scores and then map out 1, 2, and 3 standard deviations. Okay, this is the new content for the day. It's called significance testing. What significance testing is the idea that you want to strive for 95% predictability for future data, all right? So let's think about political polls, all right? If you come into Delaware County, all right, and you ask people in Delaware County who you're going to vote for, you don't ask everyone in Delaware County. What you do is you ask a random sample size of individuals within Delaware County. And the way in which you figure out how many people do I need to ask in order to get to some sort of 95% predictability for who will actually win the presidency in Delaware County is you have to know what the Delaware County population is. And then based on that population, you have to go and find a certain amount of people within a random sample to go and ask the question to who do you want to be president? Let's say it's Biden versus Trump. All right. Now, how do you know how many people to ask? Right. Well, you need to know what the population is, and I would encourage you, if you have the textbook, which hopefully you do, in the back of the textbook there's an appendice, right? Or there are appendices, right? And on page 322, they actually have a chart. Now, this is all mathematical stuff that's been worked out long before you got to this class, so don't worry about where these numbers come from, right? But there's a chart that says if your population of people you're trying to generalize is, let's say, 100,000 people. Let's say that there are 100,000 voters in Delaware County, all right? The chart on 322 will tell you, all right, in order to get to a 95% significant testing, which means you're within, plus or minus 5%, right? You have to interview at least 383 people, all right? So what this means is I go around Delaware County and I interview 383 people, and let's say that 60% of them, of the 383 people I talked to, 60% of them say that they're going to vote for Joe Biden, and 40% of them say they are going to vote for Donald Trump. Now, I can predict that Biden will win the presidency in Delaware County because even though I haven't interviewed all 100,000 people, I have interviewed a large enough sample size of individuals who are registered to vote in Delaware County in order to give me plus or minus 5% sort of in my prediction. So what this means is that I have predicted, based on my sample size, that 60% of people are going to vote for Biden. So what I am actually predicting, if there's plus or minus 5%, is that Biden's final numbers in Delaware County are going to be between 55% win and a 65% win, right, in Delaware County, right? I also found out in the 383 people that I interviewed that 40% of them said, you know what, I'm going to vote for Donald Trump, which means Donald Trump's final numbers are going to be between 35% and 45%. All right? So you have to figure out what your population is. So if you do want, and this is going to be important when it comes to like generalizing, right? So if you want to figure out who's going to be the president, let's say there's about 130 million people. Well, I guess in the last election it was closer to 150 million people. Let's just go with 150 million people. It might have been, I think it was a little bit higher, but let's go 150 million. There are 150 million people who voted in the last election, right? Now, in order to predict who's going to win the presidency, throughout the summer, what a bunch of pollsters do is they go around and they say, okay, if 150 million people are going to vote, what is the sample size of individuals that we need to get on record with regard to who they're going to vote for in order to predict who the president's going to be? So this is why months in advance, pollsters can go around and predict with some certainty or some accuracy who's going to win the presidency or who's going to win a Senate seat or who's going to win a House seat, right? They do this based on statistical probability based on a random sample, right? So again, you never are able to interview everyone in the population. But what you can do is you can interview enough of a random sample within the population to get to some sort of accuracy. And people are really looking for a 95% accuracy rate in most scientific testing, right? Scientific polling, for instance, right? So that's what people are talking about when they do these things, like Biden will win at 60%, but it's plus or minus 5%. This is why sometimes you'll see on the news, let's say that Trump is leading in the polls, 48 to 46, but there's a plus or minus 3% error rate. Well, technically, this poll is tied, right? So technically speaking, it's like, oh, the polls are tied. And the polls are tied because Donald Trump could get anywhere downwards to 45%. Joe Biden over here could have upwards of 49%. So in all reality, if something is within the margin of error, what this means is that these two numbers, even though Trump has a little bit higher number in this poll, this is actually a tie because it's within this margin of error, plus or minus 3%. All right. So again, they don't interview everybody. They interview a large enough random sample, and that large enough random sample is generalizable to the larger population. All right. So the first thing you always have to do is figure out, when you're doing quantitative research, what's my population, the total population. If I'm doing Delaware County voters, maybe there's 100,000 people. That'll give me the information. These charts are available everywhere in our classroom, in our textbook. It's located on page 322. What you do is you say, okay, the population I'm trying to make a statement about, generally speaking, has 100,000 people in it. So how many people within that population do I need to interview randomly in order to figure out some numbers that are probably very, very close to 95% accuracy with regard to predicting the viewpoint of the entire population. All right. So this gets into sometimes people overgeneralize. All right. So what this means is that sometimes people will say, well, my population is, I want to study college students, right? And there's millions of college students, but maybe they only hand out surveys to 1,000 college students on their particular campus where they happen to be a professor. And then all of a sudden they get their results back and I say, hey, I have found out that, well, I'll use this example later, but I'll use it now. I have found out that sexism is a problem on college campuses. And you say, hold on a second, and a person who has an eye for research methods, they say, hold on a second. There are millions of college students, right? There are hundreds, if not thousands, of colleges throughout the United States. You interviewed 1,000 students on your own campus, right? So your research might be applicable to your own campus, but now you just overgeneralized sexism for all of college campuses based on unsound research methods. So people tend to overgeneralize, and the reason people don't overgeneralize is because they kind of get a big head and a big ego about who they are as far as a researcher, right? So anytime you want to make sure that you sort of stay within the boundaries of what your population is and the sample that you picked from your population, if you're going to make these broad statements, right? So if you want to talk about sexism on college campuses, you might not be, based on your sample size, it's like maybe you can't say anything about sexism on college campuses, but you might be able to say something significant about sexism on your particular college campus, all right? So you don't want to overgeneralize, all right? And this is some of the problems, if we get into a little political territory right now, this is some of the problems when it comes to sort of national media, right? Not harping on the media per se, but the major hub for U.S. media is in New York City, and a little bit in Los Angeles, but mostly New York and Los Angeles are those are the big sort of coastal places. So you see people who are on these news shows, and whether it's Fox News or MSNBC, or I guess CNN is located in Atlanta, but still sort of major urban areas, right, that sort of miss large places in the country. People get on these news shows and they talk about all of these social problems in America, and I kind of look at them and I'm like, well, there might be social problems in New York, right? Because all the people on the news right now, you all live in New York City, you're all hanging around New York City, you see these problems in New York City, you're affected by, but that doesn't mean that those problems are pervasive throughout the 330 million people across large, 3,000 miles between New York and Los Angeles. It doesn't mean that they exist everywhere, right? It means that that particular problem, that, social ill that you're talking about, just might exist in your neighborhood, but it feels as if to the rest of us, because we're all we all pump the same news into our living rooms every night, it feels as if it's a problem throughout the whole USA, when really it's like a handful of newscasters who live in a couple major metropolitan areas are the ones creating this storyline of something that might be very real in their life, but they have overgeneralized it and make it a stand-in for there's this huge problem throughout the US. And it's like, it's not a huge problem throughout the US, statistically speaking. It might be, but what you can only speak to is it's a huge problem sort of in your neighborhood, in New York City. because that's where you live and that's sort of what you see on the streets every day. But you don't know what it's like in Kansas City or I don't know Cheyenne, Wyoming, Wyoming, Salt Lake City, Utah. Like these places might be very, very different. So you want to be careful to not overgeneralize issues or problems or habits or behaviors. Just because you happen to see it out your back door doesn't mean that everybody sees it everywhere else. Okay, finally, what's called a hypothesis and a null hypothesis. You just need to know this term. This will be on the next exam, right? A hypothesis is a statement. It is not a question. It is a statement with a period at the end, all right? And what you do is before you do your research, right, you make a prediction about the relationships between the variables. So if I do X, right, an independent variable, if I sort of create this catalyst, then Y will happen, the dependent variable will happen, right? If I do this, then this other thing will happen, all right? You make a prediction about the correlation between the stimuli, right, and the outcome, right? So you're making predictions about what changing the variables will do with regard to behavior, all right? A null hypothesis is a statement to test that there is no relationship between the variables. So sometimes you're going to get that sort of correlation versus causation phenomenon, right? And you might say, oh, look, I added a stimuli and this other thing happens. A null hypothesis comes in, you can test a null hypothesis because what you might find is that your stimuli actually didn't cause the thing that happened. Both of the things happened at the same time, but they're actually unrelated. So a null hypothesis helps to show whether or not causation was the reason that these two things acted in the way that they did. Yeah, all right, so let's go back to the TV causes obesity situation I gave, long ago, right? So if I watch a lot of TV, then I will put on 20 pounds. If I watch 4 hours of TV a day for a month, then I will put on 20 pounds, right? A null hypothesis tests that there is no relationship between television and eating habits. So what I could do in that experiment is I could say, okay, I'm still going to watch TV 4 hours a day, but they're going to put me on some sort of diet and exercise regimen to test that TV doesn't actually cause weight gain, that maybe it's a different variable. So there's two different experiments that are set up to test both sort of TV watching habits and exercise and diet habits and weight gain. And you're testing both hypotheses because you want to see whether or not these items are causal, right? Whether or not they cause each other or whether or not they just happen to be related, but they actually don't cause each other, all right? So a couple of examples with regard to hypothesis, you could predict going into an experiment, males self-disclose information about themselves. Males self-disclose more than females, right? You set up an experiment for that. But you could also set up a null hypothesis that says there is no difference between male and females regarding self-disclosure. All right, and you set up an experiment for that. Now you might find out that both experiments sort of prove to be true, so to speak, right? You could set up an experiment and you're like, wow, I did an experiment and it looks as if males self-disclose more than females. But I also tested the null hypothesis and I also found out in this different experiment that males and females do not, there is no difference between self-disclosure. What that tells us now is that I have some weird methods going on here. There's some variables I haven't figured out yet because both of these statements can't be true. So you put hypotheses in conflict with one another, and if after your experiment they both come out to be true, you realize that both of them can't be true at the same time. And so there is a third variable that you haven't found yet. That there's something going on in the methods in the experiment that is off. So now you have to kind of go back in and dig around. So if I only did one experiment, if I only did an experiment that says males self-disclose more than females, and I found out that to be true, and I'm like, oh yay, I'm done. I go publish it, and now all that information is everywhere. That could be bad information, right? But if I also test a null hypothesis that says there's no difference between males and females, and I find that also to be true, now I have two conflicting truths. Males self-disclose more, males and females self-disclose the same amount. And it says, don't publish either one of these papers yet, because there's some variable in here that you haven't figured out. And part of the problem what we call the replication crisis in the social sciences, is that a lot of people test just a hypothesis and they start publishing information, and you realize like all this information is bullcrap. And the reason it's bullcrap is because they didn't really dig into the methods. They didn't look for additional variables. They were like, oh, I found out the hypothesis that I predicted. I found out that it's true. I'm just going to go publish it, without sort of slowing down and saying, okay, let's test it 5 other different ways to make sure that the first results I have are actually accurate and that there aren't other variables that I've overlooked sort of in this relationship. All right. So null hypothesis and hypothesis. Know how to write one of these, each one of these. There's going to be a test question that says, here's the situation, write a hypothesis, write a null hypothesis for carrying out this experiment. All right. Okay. That's all I have for today. I'm going to stop here. It's only 20 minutes in the class, but you need to do that math. That's way back, 15 minutes ago. So make sure you do that math stuff. We will meet on Friday. We will talk about that math homework. Make a little bell curve for yourself. Make sure you know how to do the math, and I'll see you all on Friday.